All right, what do we got here? 6-8, number 5. This is hitting a stick. So we got our stick. It's hanging vertically from a hinge. It's initially at rest, and we apply a horizontal force to it in a couple different places. The first part of the problem has it apply at the bottom, and the second part of the problem has us apply it at the center of mass. So, first question is what is the acceleration of the center of mass when that force acts at the end point? Okay, so that's a torque question. It's a question about acceleration, so we should be thinking about what is the torque acting on the object if I want to know its acceleration, especially its angular acceleration. So, summing up the torques, there's only one torque. There's the weight force acting straight down, so it is parallel to the lever arm to the hinge point and applies no torque. We are applying the force horizontally, so it is perfectly perpendicular to the lever arm, so no cross product to do there. So we just have the force times the length of the stick for our torque. It's then a stick rotating around its endpoint, right? It's acting like a physical pendulum. So the moment of inertia is 1/3 ml squared. But they want us to find the linear acceleration at the center of mass. So we're going to substitute in for our angular acceleration a over L over 2, right? Because at L over 2 is where we want the acceleration to be found. So that's the distance we put in for the angular acceleration conversion. After that, it's just algebra, 3/2 force over mass. All right, so it's going to accelerate. Now, what's interesting is they're only asking about the horizontal acceleration. They're not asking about the vertical part, and they never ask about the vertical component of the hinge force, which I find interesting. So we'll get into that. So the next part of the question is, what is the hinge force acting when the force acts at the endpoint? Hinge forces are super weird, kind of counterintuitive. They're hard to envision. So what I do with hinge forces, I ask myself, well, what would the object do if the hinge wasn't there? How would it try to rotate, or how would it try to move? And then I have the hinge hold it in place. So if I hit around the center of mass, or sorry, if I hit at the endpoint and there's no hinge, the stick wants to rotate around its center of mass. Most objects do want to rotate their center of mass unless they're forced to do otherwise by a hinge or an axle. So if I push here horizontally, the top of the stick wants to move to the left. So then the hinge needs to apply a force to the right to hold that in place. So as I push here, it's trying to rotate counterclockwise. It's hard when I'm looking in the video in the mirror image. So when I'm pushing here to the right, the top wants to rotate left, so the hinge must hold that in place so the center of mass can start rotating to the right and up. So our hinge force in this case is going to be to the right. We're just going to put it into the equation as positive because technically we're always summing up forces, and then we're going to let the numbers tell us whether it's positive or negative. I can conceptualize that it's going to be to the right and it's going to be in the positive direction, but if that's a little tough for you with hinge forces, if you know the acceleration, you can just put the hinge force in as positive, and then if your answer comes out to be negative, then you know it was really going to the left, or if it comes out to be positive, you know it was going to the right. So for this one, I'm just going to put the hinge force in as positive, and I'm going to let the math do the work for me. So then I'm going to plug in my M, my A, and the force given, and I'll get my hinge force. Okay, so then if we apply the force not at the end but at the center of mass, then they ask us the same two questions. What's the acceleration of the center of mass, and what's the force from the hinge? So if I apply a force here, obviously it's going to rotate in the same direction, but with no hinge and I apply a force at the center of mass, the stick would cause no rotation, right? If there's nothing else acting on it, I've eliminated this hinge force, and I push this way, the stick won't try to rotate at all, but it will translate to the right, which means the hinge needs to be pushing to the left, so we do get that rotation. And again, we're going to put it as positive, and we're going to let the math tell us the positive or negative, but where there are ways to conceptualize which way that force is acting, right? Similar to how I think about friction, imagine what the object would do with no friction, and then have friction oppose that motion. I'm doing the same thing here at the hinge force. So here in the middle, the motion would be no rotation, so the hinge force must then act to the left, so we get a rotation. Okay? Or if we act here at the end point, the object would tend to rotate counterclockwise, and this would try to move left, so the hinge needs to apply a force to the right. Same approach then, sum of torques, boom, except now our torque is acting at L over 2, not at L, so our torque is then the force given times L over 2. Same moment of inertia, 1/3 ml squared, and they still want the acceleration of center mass. We're still using L over 2 here for our translation. And then once we know the acceleration, we can put that into our sum of forces equation, and again putting in the hinge force as positive, not giving it a direction, letting it stand, and then letting this math tell me the answer. So notice then the equation is ma minus f for both cases. In the second case, the acceleration is only 3/4 f over m, where in the first case, the acceleration was what? 1/2 3 over 2 f over m. So in the first case, we get a much bigger acceleration. Here we get a smaller acceleration, and then that actually is going to tell us the size of the hinge force. And if it's either bigger or smaller than F is originally, then the hinge force will act in the opposite direction. And the math shows us that as we put in a 1/2 here and a 3/4 here, we're going to either get then a positive and then a negative number for our hinge force. So there you go. Hopefully that helps.